Okay, so the plan for today is basically to move forward with approximate integration. We might get through all of this today, but we probably won't. So we'll probably kick part of this to the supplement along with a couple of partial fractions examples. Note that there's an integration practice review sheet posted on Blackboard now in the supplemental materials folder. So you can pop over to Blackboard, download that, and it's a little over 20 integrals. Some of them are pretty straightforward, like simple substitutions. Some of them require some of the more recent techniques that we learned. So, and they're kind of just in a random assortment. So that way you can really assess whether you understand the techniques well enough to apply them when you don't have the additional piece of information that you're working in, say, a homework set that's for this section, so you kind of know that that section's technique is the one that really is the crux of the problem. So that is available now. And as I mentioned, either later this week or next week, I'll post a video of me working through um, those integrals pretty quickly. I won't work through all of the details from start to finish for every integral, just basically for time considerations. Um, but it'll give you, it should give you enough to go on to be able to know what technique to use and how to proceed to get the answer. Um, okay, the quote of the day today, we'll get this out of the way quickly. This is from the Greek philosopher Epictetus, roughly translated as conceit of knowledge gets in the way of learning. Uh, so the challenge about with knowledge or information today, maybe 20 or 30 or more years ago, the challenge was actually acquiring or obtaining the information or the data. But today, we almost have the flip side challenge that if you go to Google and Google whatever thing you're interested in, unless it's something that's, pretty technical or pretty kind of closed-ended, you're probably going to get a whole bunch of different opinions from different folks, on different sides of the coin. And some of them might be well versed in the area and have a good argument this way or a good argument in the opposite direction. Some of them might be like conspiracy theorists, or they might be intentionally trying to mislead, or they might have other incentives that aren't aligned with yours, right? So the challenge these days, I think, is more about curating information, coming up with a set of rules or principles about um, when you're searching for something, especially something that is somewhat controversial, uh, or something that's a more open-ended question, before you look at the information, what are what are the principles you're going to apply to decide if that information should be trusted? Some people just say, oh, well, just listen to an expert. If somebody's not an expert, you shouldn't really give their opinion or their thoughts much credibility, but that just kicks the can, because then you have to define expert. And if you actually ask somebody, if they say, well, listen to the experts, or the experts say this, you say, okay, well, number one, what experts say that? They usually can't say. And number two, well, how do you define an expert? What are your criteria for deciding whether somebody's an expert? In my mind, it's almost equally as difficult to decide if somebody's an expert as it is to decide if the thing they're saying is trustworthy or not. And it's not just something like having a degree or working in the field, because you can point to lots of counterexamples of people who have a certain degree or work in a certain field actively and say things that you probably wouldn't trust. Um, so I think the best thing you can probably do in this kind of battle is to keep an open mind and be actively curious. So when you're looking for a piece of information, I mean, if you want to figure out, Excel is doing this annoying thing, how do I make it stop giving me this pop-up or something? Well, that's kind of a closed-ended question. But if it's something that's more open-ended or something that's more complex, um, be actively curious. Approach it with a stance of curiosity, where you're interested in seeing what the different sides have to say, and actively seek out, you know, if you feel like you have an opinion already on the topic, actively seek out, sources that have the opposite opinion, and, give them a fair ear, so to speak, give them a fair listen. So I think that's maybe about the best thing that we can kind of do uh, to decide what information we should trust or what folks we should listen to. All right, so moving on to section 7.7 on approximate integration. So far, our integration techniques have been, in a sense, kind of like closed-ended. We find a technique that works for this particular integral. We get an exact solution, either as a number for a definite integral or as a function for an indefinite integral, and that's our answer. What's the idea behind approximate integration? And I guess a little side note before we get into this, this this discussion, that this thing we're covering here could balloon into an entire course. It could balloon into an entire you could do an entire PhD in numerical analysis. So we're scratching the surface of a much bigger topic here. This is a bit of a crash course. This is kind of a lecture that's meant to say, hey, look at this thing that's out there that you could do. Not to say at the end of this lecture you should be an expert in this topic. So we're scratching the surface here. There are a lot of great resources on this topic, but if you're interested, you can look up something like numerical analysis and or numerical quadrature or something like that, and get a bunch more resources and a lot more information. But what's the general idea here? Well, first, let's suppose that we're looking at a definite integral, maybe something like integral 0 to 1, but it's an integral that with an integrand that we can't really evaluate. Right? I don't know an antiderivative for e to the negative x squared, and none of my tricks are going to yield such an antiderivative. Integration by parts, partial fractions, none of that's going to help. It is a fact that we're not going to prove, but so I don't know. Should this information be trusted that I'm telling you? Well, uh, but it's a fact that we're not going to prove, but there's not a closed form antiderivative for e to the negative x squared. You can't write down some, combination or compositions of sines and cosines and polynomials and things and have that be the antiderivative of e to the negative x squared. So we can't apply fundamental theorem of calculus here. I mean, we could, it applies, but it doesn't get us anywhere. So what do we do then? Well, often we're in this situation where we have either an integrand that's like this, or maybe even we just have some data from some experiment or something, and we have to imagine that there's some, f of x that we don't even know what f of x is. Maybe we can evaluate this function at some different points of time or space or whatever, but we don't even know what its algebraic structure is. Maybe we could take the data and fit a model to it. That would be one approach, and then we have an algebraic structure, but maybe we don't. But I want an answer. So let me just stick with the case where we say we do have a function. I want an answer, but I can't get an exact answer. I can't get the square root of 2 or something like that out of here. Well, kind of the next best thing, maybe in some sense, is to get an approximate answer. Whatever this may be, something like that. I'm not saying that this is anywhere close to the correct answer, but, can I get an approximate answer? If I'm looking to use this integral to do something to help me build a bridge or, design an engine or something, if I can get an answer accurate to 3 sig figs, 6 sig figs, I mean, that's probably going to be good enough, right? I mean, if I got a square root of 2, I'm not going to, design a component that has a side length square root of 2. I'm going to say it's what, like 1.414 inches or something like that. So I'm going to be doing this anyway, even if I had an exact closed form answer. If I can get an approximate answer to essentially whatever degree of accuracy I desire, that's about as good. I mean, as much as it pains me as a mathematician, I have to admit that's about as good as getting an exact answer. So from a practical standpoint, what does it matter if I say this is square root of 2, or if I say this is about 1.414? if I only need 2 sig figs of accuracy, this is plenty good enough. As a mathematician, it just feels so much more satisfying to get an exact answer, um, but we don't always need that, and sometimes we can't get that, as in this example, or sometimes maybe it would be theoretically possible, but if we had to spend 2 hours messing with a bunch of integration techniques to get the exact answer that we're just going to plug into a calculator and get 3 sig figs of accuracy for anyway, that time probably could have been better spent elsewhere, right? If I could ask a computer to give me an answer to 3 sig figs of accuracy and just be done with it in 5 seconds. So the general idea is that I have this e to the negative x squared from, say, 0 to 1. That's not quite right. 1 is the inflection point. So we'll at least make the picture look a little better. And I realized that really what I'm looking for here is an area. I'm looking for this area under this curve between 0 and 1. Now, if this was a nice area, say like a trapezoid or like a rectangle, um, perhaps even like a quadratic, or even if it was a quadratic, I could compute the area exactly. Well, if I can take this area that I'm interested in, this here, I might be able to split it up into a bunch of small chunks and approximate each of those chunks by a simpler area. Say, for instance, just a straight line at the top instead of the curvy function at the top, making a bunch of rectangles, making a bunch of boxes, add their areas together, and the areas of the boxes, right, I add all these blue areas together. Those areas are approximately equal to the area of the original area, the area under the original curve. If I use more and more boxes, I get a finer and finer mesh. My error at the top, where my curvy function is being approximated by the boxes, but not perfectly. If I use more boxes, I get less area, or I get less error in the area. I kind of filled in all of these little chunks of area up here that were errors, but now I filled them in so I have less error when I use more boxes. If I'm willing to do more work, I get more accuracy out. That kind of makes sense. So that's the general idea. I want to uh, take the geometric figure that I'm dealing with here, cut it into a bunch of different slices, approximate each of the slices with a simple geometric figure, add up all those areas of the simple geometric figures, which I can compute exactly, and that gets me an approximate area or an approximation to the original area. So that is my goal here. Another constraint is I have my function here. I want to only plug points into my function. So I have my, let me just draw this again. I have my original function here, and I have my couple of boxes like this, let's say. What's the height of this box? Well, I choose the height of my box to be a point on the function, right? If this is, say, 0, 1/2, and 1, this height here is f of 1/2. I make an assumption that I can evaluate my integrand, that function itself, that e to the negative x squared, wherever I need to. And kind of in practice, these function evaluations are going to be the most costly computer steps. So when I'm asking, how long is it going to take the computer to give me an answer for a certain number of boxes, it's basically going to come down to how many function evaluations do I have to do. Asking a computer to evaluate something like e to the negative x squared for a certain input is much, much more taxing on the processor and computer time than something like just adding two numbers together or, dividing a number by two or something like that. So when we're looking at the cost in terms of either time or computer cycles or something like that of an integration technique, we're basically just looking at number of function evaluations, right? There are other things that are costly. You might have to add things together, add numbers together, or divide by a number, but those kind of pale in comparison to most function evaluations. And obviously, we're kind of presuming that our integrand isn't just a super simple function that's really easy to evaluate, because if it was really easy to evaluate on a computer, it would probably be really easy to deal with algebraically, and we could just know what the integral was. So that is the general idea. We're trying to get a number that is an approximate value for this integral by splitting the area into approximate chunks of area that are nicer geometric shapes. And we're trying to do so in a cost-effective way with not too many function evaluations. But we, in theory, can do as many function evaluations as we need to. So this should look like a very familiar setup. This is basically just Riemann boxes. This is basically just how the definite integral is defined. So what is our goal here? Our goal is to come up with methods, and these fall in a certain category that are called Newton-Cotes methods. Just a little side note in case you're interested in looking a little further into this. The methods we're going to look at fall into this category. There are other ways to attack this problem that are different, that follow a different paradigm or different paradigmata or paradigms. But the methods we're going to look at, or the methods that are in the book, are these Newton-Cotes methods. So our goal is to ask ourselves, okay, like, how complicated of an integrand can I put in here for a certain method? So now we're looking at developing the methods. We're kind of switching gears. For a certain method, how complicated of an integrand can I put in here and have that method return an exact solution? It seems like I just went through all of this statement about how we're trying to get an approximate solution. Now I'm saying we're trying to get exact solutions. But the point is that the more complicated the type of function I can get an exact solution for, kind of roughly speaking, the better my method is going to be for very complicated functions. If I can get a method that's exact on quadratics, it's going to do a lot better on a curvy function like this than a method that's only exact on constants. There's a deeper idea at play here, but it has to do with Taylor series that we'll cover at the end of this course, so we can't quite get there yet. But we do have an inkling of this from Calc 1, the idea of linear approximations and even quadratic approximations, that we can kind of near a point of interest approximate a function, a nonlinear function, with, say, a line, and it's a pretty good approximation near that point, under some criteria, of course. And that's really kind of what's going on here, right? If I imagine considering a linear approximation to e to the minus x squared somewhere along here, if I develop a method that's exact on linears, then it'll be exact on that linear component of the approximation. It'll only be the other higher order terms that are kind of not dealt with. Or if I went a step further and thought about a quadratic approximation, something that I usually talk about in Calc 1, it's maybe not always discussed, but if I have a method that's exact on quadratics, then kind of that whole quadratic approximation bit, chopping off a little bit more of the information in that function, is going to be perfectly dealt with. And then the nonlinearity that we haven't dealt with is going to be an even higher order term. It's going to be even smaller error. So that's really the idea here. Kind of roughly speaking, we think of a function like this as being an infinitely long polynomial. And the more of those terms that we can chop off and handle exactly, then the more accurate we get. We're never going to get completely accurate because there's always more terms that we haven't handled yet exactly. But the more of those terms, constant, linear, quadratic, etc., that we can handle exactly, the more accurate our method is going to be, because the more information in that function we're dealing with exactly rather than approximately. Okay, so what is the idea of Riemann sums? The idea of a Riemann sum, let's take a right Riemann sum, for instance. And let's say that I break my interval, let's say from 0 to 1, into widths delta x. Or in this case, maybe I'll use n equal 4 boxes. So the number of boxes will be 4. And delta x is the interval width, b minus a, or in this case, just 1 minus 0 over n. As a little aside, I don't think I say it explicitly down here. No, I don't. As an aside, without loss of generality, uh, we can change the bounds on our integral, right? This is just a simple substitution. Changing integral a to b to integral 0 to 1 is just a question of, doing a little substitution. Or we could change to integral minus 1 to 1. These are two convenient start and end points, upper and lower bounds for our integrals that we'll be using in some of these calculations. So, we'll write a to b here because it's the general case, but we could do just a little u substitution, translate this into integral 0 to 1 of some other function, and we have a nicer interval to work with. So the intervals that I'll demonstrate are going to be on 0 to 1, just so I don't have to, number one, write a whole bunch of a's and b's, and number two, don't have to keep track of like the a plus I delta x and all that kind of stuff. Just makes it a little nicer to start at 0 and end at 1. So my delta x, my interval width here, is going to be then 1/4, because I'm using 4 Riemann boxes on an interval width 1. On each of these intervals, from 0 to 1/4, from 1/4 to 1/2, etc., I'm going to approximate my curvy black function by just a constant function. Right? So my Riemann sums, whether left or right, say, okay, just for a right Riemann sum, take the right endpoint of this first interval, evaluate the function there. This is f of 1/4, for instance, and then approximate this first black chunk of area, the area under the black curve between 0 and 1/4, approximate that with this rectangular area, this green area, that's this rectangle between 0 and 1/4, and with height f of 1/4. I'm just approximating the black function here with this green constant function. This green constant function is f of 1/4 the whole way across. And we'll call this maybe area 1, something like that. Do the same thing here, area 2, height f of 1/2, area 3, f of 3/4, and area 4, our box has height f of 1. I see each of my boxes has area, for instance, area 1, is width, delta x, times height is f at the right endpoint. So for instance, f at 1/4. Area 2 is delta x, f at 1/2, and so on. Or I just end up with the total area, the total green area, adding up all the areas of the boxes, is delta x times f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1. And we often call this something like maybe R4 for the right Riemann sum using 4 intervals or 4 boxes. Now here we can kind of visually see that if we use more boxes, for instance, if A2 was split into 2 boxes, say 2 red boxes, on the right side over here, the right half, I don't really get any additional accuracy, but on the left half, I get to fill in a little bit of the area up here that otherwise would have been error. So I can visually see that the more boxes I use, the more accurate I get. However, also the more boxes I use, the more function evaluations I have to do. If I use twice as many boxes, it's going to take my computer about twice as long to complete that approximation. Okay, so this is the right Riemann sum. The left Riemann sum does almost the same thing. It just takes the left endpoint. Let me use maybe blue for this. Takes the left endpoint as the proxy for the height of each box. And we actually might notice that most of the green right endpoints correspond to blue left endpoints for one box over. It's actually mostly the same function evaluations, right? If I was using the left Riemann sum, I would have delta x times f of 0 plus f of 1/4. F of 1/4 would be my area 2 height instead of my area 1 height, plus f of 1/2 plus f of 3/4. My left Riemann sum actually just swaps one endpoint function evaluation for the other is practically all that it does. Right? I have an f of 0 here instead of having an f of 1 there. But the majority of the areas end up being basically the same area, even though they look quite different. Both of these methods are so-called first order. What does that mean? So if n goes to say 2n, if my number of boxes, if I do it once with a certain number of boxes and then double the number of boxes and repeat the computation, my cost doubles. Or if n went to 10n, my cost is 10x. It takes about 10 times as long. It takes a length of time to complete, or an amount of computer cycles to complete that's proportional to the number of boxes, because that's the number of function evaluations that we're doing. And remember, function evaluations are really the most costly bit of all of this. What about my accuracy? I think that as I put in more effort and use more boxes and incur more cost, my error should go down. So the error that I experience with 2n boxes, let's say absolute error, is going to kind of look like 1/2 of the error experience with n boxes. Now, this is a bit hand wavy. It's really the upper bounds of the absolute errors that follow this kind of a progression. So could you decrease the number of boxes and actually increase the error? It could happen if you started off way under the cap for the error and the cap went down, but something wonky happened, you could get more error. So it's not a perfect guarantee, but the cap is going down. The maximum absolute error is decreasing like this. Or the error, if I use 10 times the number of boxes, is going to look like 1/10 the error if I use a certain number of boxes. Or kind of, very roughly speaking, if I want one more decimal place of accuracy, I have to do 10 times the amount of work. So one decimal place of accuracy, I have to put in 10 times the amount of work. If I ran the program with a certain number of boxes and got 3 decimal places of accuracy, I think that's what my accuracy was. If I want 4 decimal places of accuracy, uh, I want to increase my number of boxes by a factor of 10, and it's going to take my computer about 10 times as long to run that task. If I want 2 more decimal places of accuracy, it's going to be 100 times as long, 100 times as much effort. Okay, so Riemann, left or right Riemann sum, has a huge benefit in that it's very simple geometry. It's very easy to understand boxes. It's a pretty easy thing to program. You just have a loop, right? Like a for loop, and it just steps along f of 1/4, f of 1/4 plus 1/4, f of 1/2 plus 1/4, and so on, and just evaluates the function, adds them all up, and then might as well just multiply by x one time at the very end, save ourselves from doing a whole bunch of multiplications. So it's basically just, one block of code that's a for loop, and that's pretty much all that it is. I mean, obviously there's a bit, have to multiply by x or by delta x, tell it what f is. And so there's, a few more lines, but the lines doing the work is basically just one block of code, one for loop. Not too bad. So Riemann is simple to understand. It's conceptually simple. It's simpler to analyze. It's simple to construct and it's simple to program. But for each decimal place of accuracy I want to get, I have to do 10 times the amount of work. What about the midpoint rule? Let's approach the midpoint rule from 2 directions. Let's have our same integral from 0 to 1. Let's use 4 boxes again, or 4 intervals. And here I look and I say, well, if I have a function that is increasing or decreasing, even if it's a straight line, my Riemann sums, if my function is a straight line, my Riemann sums are either going to always overestimate or always underestimate. If it's a straight line that doesn't have slope 0, that's not just a constant function. But maybe I look at this and I say, well, if I can kind of split the difference between these, I could kind of have some underestimation and some overestimation. If I take the height for each box to be the midpoint, to be the height of the function evaluated at the midpoint. So could I track my midpoint up here, make that the height of this first box, this midpoint the height of the second box, right? Taking the midpoint of each of these intervals and evaluating the function there. And I might maybe see most clearly in this box, I have a bit of underestimation here, so a bit of like negative error, but a bit of overestimation here, a bit of positive. Those kind of cancel out. So if I use my midpoint of each interval instead of the left or right endpoint, it feels like I can do a little better. And in fact, we can show that this is true. So let's consider, let's try to make to develop a method that is exact on 0 to 1 using just one box. So if I integrate 0 to 1 of mx plus b, this is m over 2 plus b. All right, we get mx squared over 2 plus bx, evaluate that from 0 to 1. We get m over 2 plus b is what we get. So for a linear function, this area is exactly m over 2 plus b. That's just what it is when I do the integral. This is, here's f of x. Let's say f of c times delta x for, or times a weight for what value of weight and what input here. Since we're looking at the midpoint, let's just presume that this is 1/2. So this is w f of 1/2, or this is w times m over 2 plus b, and I see that w is 1. So if I pick the point of evaluation to be the midpoint, and if I pick the weight to just be 1, kind of a boring weight here, we'll see in the future we'll get more interesting weights. Well, then I end up with exactly my m over 2 plus b. My approximation using this midpoint rule is exact on linears. The area under a linear function can be found exactly by using the quote approximation via the midpoint rule. This is kind of interesting, right? Because a linear function actually has 2 degrees of freedom, but a midpoint rule is actually only evaluating at 1 point in that interval. In a sense, it kind of doesn't feel like it should be enough freedom over here, just picking 1 point of evaluation to handle 2 degrees of freedom, but the symmetry of the problem allows for that. The symmetry helps us out here. So what is our midpoint rule? Well, what we would do here is we would say, okay, so now I have a rule that says on each interval, evaluate the function at the midpoint. And here, this weight, this 1 represents 1 minus 0, it represents the interval width. If I had a more complicated function, right, something like this, and I wanted to use more blocks, 0, 1, 2, 3, 4, I would take my 0 to 1 block, use the midpoint rule. This would be exact on linears. Then look at the 1 to 2 block, use the midpoint rule again on this bit. I would just kind of chain them together, right? Chain together these different midpoint rules on a single block to make a bunch of these blocks. And what do I end up with? I end up with f at each of the midpoints, which this is just saying take the midpoint of each interval. It's just really annoying to write it. I'm trying to select the right thing here and it's not cooperating, but it's just really annoying to write it down algebraically. But this is really just f evaluated at the midpoint of each interval, which we'll just call xi bar. That's the height of each box. Then multiply by the width of each box, add those up, and that is our midpoint rule. The error looks kind of like this. The error is related to the second derivative of the function. The midpoint rule is what we call a quadratic method. So let's come over here and look at our cost and accuracy like we did with Riemann, but let's look at it for the midpoint rule. So what is the cost? If I have a certain number of boxes that I use, and let's just say increase it by a factor of 10, if I use 10 times as many boxes, each box needs one function evaluation. So my cost increases by a factor of 10 if I use 10 times as many boxes. But here's the magic of this. If I use 10 times as many boxes for the midpoint rule, what does my accuracy look like, or what does my error look like? In other words, what does the error look like for 10 times as many boxes? It looks like 1/10 squared. Yeah. This is called a quadratic method because there's a second power here. That second power was not there up here. This was a 1/10 to the first power. It was what we would call a linear method. If I do 10 times the work, I get to cut my error by 1/10. Or if I want one more decimal place of accuracy, I've got to do 10x work. Over here, if I do 10x work, I get about 2 decimal places more accuracy. There is a downside. I mean, this is a little bit more complicated to program in, so the complexity is a little bit higher. But it actually feels just like Riemann. It's just that I'm making a box that has the height of the midpoint instead of the height of the left or right endpoint. Now, I do want to be clear about something. In theory, whether if I use left Riemann or right Riemann or midpoint or whatever, and take the limit as n goes to infinity, they all come out to be the same integral. They all come out to be the same value. Doesn't matter whether I use left or right or midpoint or a randomly chosen point in each interval. If it converges, it converges. They all converge to the same number. But the question is, if I use a certain number of boxes, if I use 100 or 1,000 or 10,000 boxes, not taking the limit as I go to infinity, which method is going to be better? Well, if I use a certain number of boxes, since if I do 10x work, I get 2 decimal places of accuracy with midpoint rule, and I only get 1 with a left or right Riemann sum, midpoint rule is probably going to be better. The downside of the midpoint rule is that I'm evaluating at these midpoints, and I might have actually chosen my interval cutoffs specifically because I maybe have experimental data at those points, and maybe I don't have experimental data at the midpoint. So maybe I can't evaluate my function there. So there are some trade-offs here. I'm using midpoints, so it's a little bit of a wonkier point to use, but the overall complexity, it's just still one for loop, right? If I look at this compared to this, it's essentially the same program. I'm just changing what my specific inputs into X are and into F are, but I'm doing the same number of inputs, the same number of function evaluations. It's pretty much the same complexity in code. I just have to deal with this kind of wonkiness of the midpoint. Okay, so what about the trapezoid rule? The trapezoid rule starts out with the goal of basically what the midpoint has as a goal. The trapezoid rule is going to consider two endpoints, two function evaluations. And create a line between them. It's going to approximate the function between these 2 points with this line between them. The left and right Riemann sums and the midpoint rule all approximated the function with a constant function, or by piecewise constant functions. Right, my black curve is piecewise constant, piecewise constant, piecewise constant for the approximation, whether I'm in midpoint, left, or right Riemann sum. I'm always approximating my original function by piecewise constants. The trapezoid, I'm actually using a linear. I have another degree of freedom. So I desire to have exactness on linears. I think I should be able to do that because with trapezoid, I'm using a linear, your piecewise linear. If I have a linear function and I'm approximating it by a linear function, it should be an exact approximation. I should get an exact answer out of here, out of this approximate method, because I'm using a linear function to approximate a linear function. Of course, it's going to be a perfect so-called approximation. Again, this is m over 2 plus b. And on the other hand, I want this to be w1 times f at 0 plus w2 times f at 1. I want it to be some weight, some number multiplied by this function output, plus some number multiplied by this function output. Essentially, I'm taking a weighted average of the two endpoints, or the points under consideration is really kind of what I'm doing here. We're not really calling it a weighted average, but that's really what it is. But what's f of 0? That's b. And what's f of 1? That's m plus b. So what do I have? I have that 1/2 m plus b. I want to be equal to w2m plus w1 plus w2 b. Well, w2 has got to be a half. And then w1 plus w2 has to be 1, so w1 has to be 1/2 as well. So w1 and w2 are both 1/2. In other words, I just average these two heights. Wait, if I average the heights and multiply by the base width, that's just the area of the trapezoid. We can look at this geometrically, we can look at it algebraically. I'm going through the algebraic structure here because when we get the Simpson's rule, we're going to be really reliant heavily on the algebraic side of things. So nicely enough, in trapezoid rule and midpoint rule, we can look at the geometric side to find the area, or look at the algebraic side to find what weighted average should I use, and it's exactly the same as we'd expect from the area of a trapezoid. Should make those slashes blue. So the geometric and algebraic sides mesh nicely together. Simpson's rule is going to be a little more complex, so we're going to be leaning on this algebraic notion over here. So if I was to apply the trapezoid rule kind of sequentially, right, I would evaluate this and I would have 1/2 f of 0 plus 1/2 f of 1 for the first block. For the next block, I would have 1/2 f of 1 plus 1/2 f of 2. For the next block, I'd have 1/2 f of 2 plus 1/2 f of 3. So I see that the right endpoint of the first block is the same as the left endpoint of the second block, so that the interior points get counted twice, and my extreme endpoints get counted once. So that's where this comes from. This 1/2, I have my delta x is, of course, my base width. This is my delta x. I'm kind of forgetting about the delta x everywhere. That's what the 0 to 1 scaling that out does. It makes the delta x go away, basically. But the delta x is the base width if I was on an interval a to b. The 1/2 comes from factoring a 1/2 out of all of these. And then I just have 1 f of 0 plus 2 f of 1 plus 2 f of 2 plus 2 f at each of the interior points. So here's my leftmost endpoint, 2 of these interior, because that's the right endpoint of the first block plus the left endpoint of the second block. Then the right endpoint of the second block and the left endpoint of the third block, and so on until we get to the very end. This rightmost guy has nobody to pair with, and it's by itself again. The trapezoid rule was designed from first principles to be exact on linears. It is exact on linears. It actually has the same behavior as the midpoint rule. The trapezoid rule essentially works the same way as the midpoint rule. The little details with some of these constants and things do look slightly different between the two, but they both basically depend on the size of the second derivative of the function we're integrating, and they both have these same behaviors as I increase the amount of work I do. If I do 10x work, if I use 10 times as many boxes, 10 times as many function evaluations, I get something like 2 decimal places more accuracy. So midpoint rule and trapezoid rule work very similarly. Note that there's some magic in the midpoint rule here. I'm able to get linear accuracy. Of course, I got linear accuracy in the trapezoid rule. I mean, I used a linear function. Of course, it's going to be exact on linears. But the midpoint rule, I got linear accuracy out of a constant approximation. I'm taking advantage of the fact that a linear function, if I pick exactly the midpoint to make a constant approximation, this triangle, this negative error, and this triangle, this positive error, exactly cancel out. That's contingent on me picking this exact point for evaluation, this exact midpoint. If I pick the left endpoint or the right endpoint, then I'm down to a linear, or sorry, a first order method, like the left or right Riemann sums. But if I pick the point of evaluation just right, I can impose some symmetry. I can get a free order. I can get what should be, what should feel like a first order method becomes a second order method. Trapezoid creates a second order method basically from first principles. And what we'll see with Simpsons, it'll feel like we should get a third order method. But because we're choosing things in kind of the way that we chose them for midpoint rule, we'll actually get a free jump. It feels like it should be a third order method, but it'll actually be a fourth order method. What that'll mean is that if I put in 10x amount of work, my accuracy, 10x work is associated with 4 decimal places of accuracy. So Simpson's rule is probably the most complex rule that's normally used, because to do 10 times the amount of work and get 4 decimal places of accuracy, I mean, a normal computer, like if you're not doing, you know, complicated programming, it can only get about 15 decimal places of accuracy. So if I'm getting 4 more for each time I multiply the number of boxes by 10, like I can only do that a few times before I'm at the limit of what my computer can hold, unless I'm doing something really specialized. And how many decimal places of accuracy do I even really need? You know, maybe four, probably not eight. So, uh, so if I were to go more complex than this and try to build a higher order method, you can do it. You can keep on building more complex methods. We can see that it starts to kind of become a pain to program and starts to become a real pain to find the actual closed form of this method. Um, Also, Simpson's rule, the error is related to the fourth derivative. It's going to be exact on cubics and anything lower order than that. Um, right. So the Simpson's rule gets that kind of free jump. If I was to build up one more level of complexity from Simpson's rule, it would be like going from midpoint to trapezoid. I got the free jump in midpoint. Trapezoid, I just added maybe some complexity in some sense, but it's still the same level of accuracy, kind of roughly speaking. Simpson gets that free jump. If I went one above Simpson, I think that might be called like the Simpson's 3/8 rule or something. It's the same level of accuracy. I'd have to go one more still, introduce a lot more complexity to really get any tangible benefit. Another nice thing about Simpson's method is it turns out, and we'll do the discussion of Simpson's method in the supplement, so we don't have time to work through the details here. But it turns out that Simpson's method using two n boxes is like a weighted average, can be exactly written as a weighted average of the trapezoid method and the midpoint method using n boxes. So 1/3 trapezoid with n boxes plus 2/3 midpoint with n boxes gives us Simpsons with two n boxes or two n, interval divisions. So that means that if I have a trapezoid and midpoint rule program, if I have one of each of those programs already programmed up, they're not super hard to program, right? Just a bunch of function evaluations. And this one, we need a couple of special end cases for the first and last, but the rest of them are just a bunch of function evaluations added up and then multiplied by 2. I can compute Simpsons this way and avoid this crazy 4-2-4-2 business that might be a bit of a pain to program into a computer. So I can even just use a weighted average of the simpler to program trapezoid and midpoint rule and get Simpsons from that. It's just the way that the algebra works out for these summations. But again, more details on that. Where do these like 4-2-4-2 kind of strange things come from? And then maybe an example in the supplement. All right, let me end the recording.